Have you ever really looked around? Circles are everywhere. Look at a clock, see that round face? That's a circle telling time. How about a bicycle? Those wheels are circles helping you move. Even a simple button on your shirt is often a circle. Circles are one of the most basic shapes in geometry. They're also one of the most important. We see them in nature like the sun and the moon. We see them in art and architecture. Circles are even used in engineering and technology. Why are circles so popular? Because they're simple, elegant, and incredibly useful. They're also really cool to learn about. In this chapter, we're going to dive into the world of circles. We'll explore their properties, theorems, and real-life applications, so buckle up and get ready for a circular adventure. Let's start with the basics. What exactly is a circle? A circle is a round shape where every point on the edge is the same distance from the center. Think of it like a perfectly round pizza. The center is where you'd hold it, and every point on the crust is the same distance from your hand. Now let's talk about some important parts of a circle. First up is the radius. The radius is the distance from the center of the circle to any point on the edge. It's like measuring from your hand to the edge of the pizza slice. Next we have the diameter. The diameter is the distance across the circle through the center. It's like measuring the pizza slice from one side of the crust to the other, passing through your hand. The diameter is always twice the length of the radius. Finally we have chords. A chord is a straight line that connects any 2 points on the edge of a circle. Imagine slicing the pizza from one side to the other, but not through the center. That slice line is a chord. Understanding these basic parts of a circle is key to unlocking all the cool theorems and concepts we'll explore in this chapter. Chords aren't just lines cutting through a circle. They actually play a role in creating angles. Remember that an angle is formed when two lines meet at a point. Now, imagine two chords intersecting inside a circle. They form an angle, right? Well, there's a special relationship between this angle and the arcs of the circle that the chords cut off. This relationship is described by Theorem 9.1. It states that the measure of the angle formed by two chords intersecting inside a circle is equal to half the sum of the measures of the intercepted arcs. Let's break that down. An arc is a portion of the circle's edge. When two chords intersect, they create two arcs on the circle. Theorem 9.1 tells us that if we add up the measures of those arcs and divide by 2, we get the measure of the angle formed by the chords. This theorem is pretty cool, right? It connects the world of angles and arcs in a surprising way. Ready to see Theorem 9.1 in action? Let's do a hands-on activity. You'll need a compass, a protractor, and a ruler. First, using your compass, draw a circle on a piece of paper. Next, draw two chords that intersect inside the circle. Use your protractor to measure the angle formed by the intersecting chords. Now use your ruler to measure the lengths of the two arcs intercepted by the chords. Remember, the arc length is the distance along the circle's edge. Add the two arc lengths together and divide by 2. Compare the result from step 5 to the angle measurement from step 3. They should be equal. This activity shows you that Theorem 9.1 isn't just some abstract idea. It's a real relationship that you can measure and verify yourself. Section 5. Perpendicular bisectors. Dividing lines with precision. Have you ever needed to divide a line perfectly in half? That's where perpendicular bisectors come in handy. A perpendicular bisector is a line that cuts another line into two equal halves and forms a right angle or 90 degrees with it. Now, how do perpendicular bisectors relate to circles? Well, there's a special relationship between a chord and its perpendicular bisector. If you draw the perpendicular bisector of a chord, it will always pass through the center of the circle. Let's try a quick demonstration to see this in action. You'll need a compass, a ruler, and a protractor. First, draw a circle using your compass. Next, draw a chord inside the circle. Then, use your ruler to find the midpoint of the chord. Draw a line that passes through the midpoint of the chord and is perpendicular to it. You can use your protractor to make sure the angle is 90 degrees. You'll notice that the line you drew, the perpendicular bisector, passes through the center of the circle. Section 6, Equal Chords, Equal Distance Theorem 9.5 explored. We've seen how chords can create angles and how perpendicular bisectors relate to chords and the circle's center. Now let's explore another fascinating relationship described by Theorem 9.5. Theorem 9.5 states that equal chords of a circle are equidistant from the center. This means that if you have two chords that are the same length, they will be the same distance away from the center of the circle. Think back to our pizza analogy. Imagine slicing the pizza into two slices with the same crust length. Those two slices would be the same distance from your hand in the center. Theorem 9.5 tells us that this relationship holds true for any circle and any two equal chords. It's a powerful concept that helps us understand the symmetry and balance inherent in circles. Section 7. Angles and arcs. A theorem for all seasons. We've already seen how chords can create angles inside a circle. But what about angles formed at the center of the circle? These angles have a special relationship with the arcs they intercept, and Theorem 9.7 explains it all. Theorem 9.7 states that the measure of an angle subtended by an arc at the center of a circle is double the measure of the angle subtended by the same arc at any point on the remaining part of the circle. That sounds like a mouthful, but it's actually quite simple. Let's break it down. An angle is subtended by an arc if its sides pass through the endpoints of the arc. So, if you have an angle at the center of the circle, it intercepts an arc on the circle. Now, imagine picking any point on the circle outside of that arc. If you draw lines from that point to the endpoints of the arc, you create another angle. Theorem 9.7 tells us that the angle at the center is always twice as big as the angle formed at the point on the circle. This theorem highlights the unique relationship between angles at the center and points on the circle, all connected by the arc they share. Section 8. Cyclic quadrilaterals. 4 sides, endless possibilities. Let's move from angles and arcs to a special type of quadrilateral that lives inside a circle. The cyclic quadrilateral. A cyclic quadrilateral is a 4-sided polygon where all 4 vertices lie on the circumference of a circle. What's so special about cyclic quadrilaterals? Well, they have some pretty cool properties as described by Theorem 9.10. This theorem states that the opposite angles of a cyclic quadrilateral are supplementary. Supplementary angles are 2 angles that add up to 180 degrees. So if you have a cyclic quadrilateral, the opposite angles will always add up to 180 degrees. This property leads to some interesting geometric puzzles and proofs. Cyclic quadrilaterals show us that when we combine circles and polygons, fascinating relationships emerge, opening up a world of geometric possibilities. Section 9. Circles in action, from Ferris wheels to pizza. Circles aren't just theoretical shapes confined to textbooks. They're all around us, playing vital roles in our daily lives. Think about a Ferris wheel. It's a giant circle that rotates, giving us a thrilling ride and breathtaking views. The circular shape is what allows for the smooth, continuous motion. Or consider the wheels of a car. They're circles that roll, making transportation possible. The circular shape ensures that the car moves smoothly and efficiently over the ground. Even something as simple as a pizza cutter utilizes the properties of a circle. The circular blade ensures a clean cut and allows us to divide the pizza into equal slices. From giant structures like Ferris wheels to everyday objects like pizza cutters, circles are essential to our world, making our lives easier, more efficient, and a lot more fun. Section 10. Geometry. Your key to unlocking the world. Congratulations, you've journeyed through the fascinating world of circles, exploring their properties, theorems, and real-life applications. We've covered everything from basic parts like radius and diameter to complex concepts like cyclic quadrilaterals. Remember, geometry isn't just about memorizing formulas and theorems. It's about understanding the shapes and patterns that make up our world. It's about seeing the connections between seemingly different concepts and appreciating the elegance and beauty of mathematics. So keep exploring, keep questioning, and keep looking for circles and other geometric shapes in your everyday life. You'll be amazed by what you discover.